Okay, so on to the last lesson, or last video, I guess. So this is the next two gas laws: Avogadro's law, ideal gas law, and looking at how you can apply the ideal gas law to gas law stoichiometry. Of course, since we did Unit 3, then we apply stoichiometry to each topic. Okay, so Boyles, Charles, and Gay-Lussac's developed hypotheses about how gases behaved without having any idea about particles, molecules, entities. So, like I said, they made their laws on really simple experiments. Okay, so if we were in class, we could do things like use a syringe, push it against your thumb, and you can prove Boyle's law. You don't need fancy experiments to do these. And the first scientists really worked a lot with gases because they were everywhere and easy to collect. And you could do a lot with a small volume. So then once the idea about particles and molecules and entities and moles came about, then there was proposed by Avogardro his law of gases. So if you have an equal volume of gas at the same temperature and pressure, because now, of course, you know that change in the temperature and pressure can influence the volume of a gas, then they will contain the same number of molecules. So it's a direct relationship. So the formula down here looks similar to Charles and Gay-Lussac's law, which were when volume increases, so does temperature, and when pressure increases, so does temperature, or vice versa. So this is a simple way to predict the volumes of gases either as reactants or products as they are involved in a chemical reaction. So the volume of a gas and the number of moles of gas present is directly proportional, of course, when temperature and pressure are constant. So in this little picture, if you have 1 mole of gas that occupies 1 liter, then if you increase it to 2 moles, then you're going to increase the volume the same amount, so to 2 liters. Okay, so we'll do 2 different examples. One where you're already given moles, and then one where you have to calculate moles, basically. So we have 0.75 moles of helium gas occupies a volume of 1.5 liters. So the first amount of moles is 0.75, and the volume is 1.5 liters. What volume will 2 moles, or 1.2 moles, occupy? So we're looking for the new volume. So this looks really similar, like I said, to the other direct relationships that we looked at. So again, the moles will cancel. Sorry, I just did that upside down. Moles cancel, and you're left with volume. So again, decide if you want to cross multiply or do 1.5 divided by 0.75 and then divide by that number by 0.7 and then multiply that number by 1.2, or if you want to cross multiply, .4 liters. Okay, so pretty straightforward. This example is a tiny bit tricky. It says it's not tricky. There are a few more steps. So a balloon with a volume of 34.5 liters is filled with 3.2 moles of helium gas. To what volume will the balloon expand if another 8 grams of helium is added? And then again, pressure and temperature remain constant. So similar to the other questions, we can't use grams and compare it to moles, right? So we have to find moles first. So we're given mass. Just to save space, I'm going to keep going, sorry. Helium that's the gas, helium, He. It is not diatomic. So you get 2 moles. And then, so now we have a mole amount. Okay, so we have our first volume, 34.5 liters, is filled with 3.2 moles. And then what will our second volume be if it expands? So now you're adding to it. So if we just write down here 2 moles, that doesn't really make sense, because you're adding that mole amount to the old mole amount. So this time you actually have to add it to it. So this question is worded a little bit differently, so just watch out for that. But it does make sense if you think about the original moment, which is this, that if it's expanding, then you should, according to Avogadro's law, you should be able to, you would have a greater mole amount than the first one. So you can think of it, look at the logic as well of the math you're doing. Okay, so again, deciding, what you're going to do here. The moles cancel again. I don't know why I'm always solving for volume. It doesn't have to be like that, but it seems like all the other questions from the last lesson too were like that. So you should get if you have a greater mole amount, you should get a greater volume, which you do. That's a 1. Okay, not so bad. Okay, so the ideal gas law is this thing in this purple or pink bubble here, PV equals nRT. So what happens when you do want to consider a mole amount of a gas? And then, so we're going to relate this also to stoichiometry, which is of course useful. Let's say if you know how much mole or how many moles of gas you're starting with, how many moles of gas are you going to get produced, right? So then this ideal gas law is the only law that has moles and pressure and volume and temperature. So again, now you're incorporating all of the variables and how they change. So when they discovered that 1 mole of gas occupies 22.4 liters, if we were at school, we have a box that represents 1 mole of gas. So it's not a very big amount compared to, say, 1 mole of copper or 1 mole of desks or 1 mole of students, something like that. It's a small amount still. And we want the temperature to be in Kelvin. And what they noticed was that when you have 1 mole of gas, which occupies 22.4 liters and standard pressure, then they kept getting this universal gas constant, this number that came out of the relationship. So that is called the R value. So it is on the back of your periodic table if you choose to keep that with you. Noticing that because you're given this value, it's actually pretty helpful. It tells you the temperature has to be in Kelvin, of course, moles, and then it tells you that the pressure has to be in kPa and that the volume has to be in liters. Okay, so you just want to, when you use the ideal gas law, you just want to make sure of those things. Volume has to be in liters, pressure kPa, moles is moles, and then degrees Celsius in Kelvin if you're going to use this universal gas constant. Again, should you continue in chemistry and choose to move forward, then you'll find that there are other forms of the gas law. There's one with using atmospheres. So just check your units when you're doing your questions. Okay, so this question, a container contains 1.45 gram sample of nitrogen gas at a pressure of 0.45 torr and 22 degrees Celsius. So it doesn't really talk about how the pressure is changing, how the temperature is changing. You're given an amount. So this is mass. So this is a bit of a unique question that we haven't really dealt with before. And then B, it says if the sample in A reacts with oxygen producing nitrogen dioxide in a 5-liter container at 22 degrees Celsius, what would the pressure of NO2 be? So we are going to take the sample in A, which is nitrogen gas, and change it into and look at figuring out a different variable for nitrogen dioxide as a part of a reaction, which of course is stoichiometry. Okay, so the ideal gas law, because it does incorporate moles and all of the other variables as well, then this is a useful formula when you're trying to look at an analysis of a system that is undergoing a reaction. Okay, so let's do A first. If you print the note off, the B is on the next slide, so we can just do A on here. So you need to remember that nitrogen gas is diatomic. Okay, so that's why I like this question at the end of the year. It's kind of good review for the exam if we're having one. And then we need to change the mass into moles again. So N2's molar mass is 28. Okay, so now we have moles. Of course, we have R. And so remember these units here. Tell you what the units need to be then for all the other pieces of information. So volume, that's actually what we're looking for. Pressure has to be kPa. So we are given torr, which means we have to convert it into kPa. So this is where you're going to use that conversion line, which is for pressure, which is either on the first day's note of this section or on the back of your periodic table. And we used a ratio. So how many kPa when you have 0.45 torr? And then if you look on that conversion line, you're going to get 101.3 kPa for 760 torr. Okay, and then again, decide how you want to solve. Okay, and then we have temperature. So this all goes with pressure. Temperature is 22 degrees Celsius, and then here we need Kelvin. So you add 273, 295 Kelvin. Okay, I'm just going to change to now sub it in. So PV equals nRT. Unfortunately, this law often gets the, the silly saying to try to remember it as the pervert law. So I guess whatever floats your boat, okay? PV equals nRT is the ideal gas law. So our pressure is 0.05998 kPa. What's the volume going to be? Our mole amount, 0.0518 mole. 8.314. I'm running out of room, so I'm not going to write the units. Okay, so what are we doing with the temperature here? We have well, you know what? Let's just do volume and pressure, okay? Because we're looking for volume. If we have a really low pressure, then that means the volume should be quite large, okay? So you're going to get, when you do 0.0518 times 8.314 times, actually, I'll show my work here. So 0.0518 times 8.314 times 295, that gives you 127.046. So you get 2,000 liters, which seems like a lot of liters, but we do have a really tiny pressure. So pressure and volume are inverse, right? So that's not outrageous. Okay, so let's do B. So if the sample in A reacts with oxygen, so we have N2 plus O2 making NO2, then we need to balance that. So 2 nitrogens on the left means we need 2 nitrogens on the right, but then that made 2 times 2 times 2 is 4 oxygens, so we need a 2 there. It says the sample from A, so that means we have 0.0518 moles of nitrogen. Reacts with oxygen in a 5-liter container, 22 degrees Celsius still. I'll just show my work again, even though we already did that one, that would be fine. And then, of course, R is given. And we are looking for the pressure of nitrogen. So now nitrogen and nitrogen dioxide do not have the same coefficient, so we have to do stoic first. Okay, so because we're asked to find the pressure of NO2, we need the moles of NO2. That's our X value. In the bottom goes its coefficient. And then we have the moles of N2 and its coefficient. Now, as you've gone along here, you might use shortcuts. You might not need to write the coefficient part at the bottom. You might not need to write mole NO2. You can make shortcuts, but just make sure you're making those shortcuts correctly, that's all. So there's twice the amount of moles because it's got a coefficient of 2. That's 2 times that. And now we can have all the variables to do the ideal gas law. I'll just pick a different color so it sort of stands out. Can I make more room? Yes. So again, because we're finding the moles, or we are asked to find the pressure of NO2, then we have to use the moles of NO2, okay? That's what that is. And then the R value, and the temperature was 295 Kelvin. $50.82 kPa. Okay, so now again, our volume is much bigger, 5 liters, so then the pressure has come down quite significantly. Okay, so that's it. Take a look at the homework, and I'll post the gas assignment soon. So thank you, and let me know if you have any questions.